Thanks, Jeremy. Yeah, I appreciate you being with a short introduction. Hi, Anastasia, and hopefully some other people will roll in. Just a quick bit of an introduction, a little bit more about myself before we get to the slides. So my name is Ryan Hazinski. I currently I'm the head of protocol partnerships at an enterprise grade infrastructure provider called Global Stake, and we'll talk a little bit about what that means maybe when we get deeper into the slide deck. But I was a high school teacher for 20 years, taught a lot of different subjects, basically just a nerd, really interested in technology, and sort of got involved in crypto and blockchain back in 2017, and then really went down the rabbit hole when COVID happened. And I left the teaching, I left the classroom, but I actually also work part-time as the Ardent blockchain education liaison. And that's why I'm doing this work. And really grateful for Jeremy reaching out to me. We've been planning this webinar for quite some time because been interested in bringing blockchain education to Florida's teachers and students. So that way they can kind of have a competitive edge moving into the future, understanding this technology and how it's going to be a big part of their future. Then more importantly, with Jeremy's work with CyberFlorida, we really kind of created a slide deck that shows the connections between blockchain technology itself as well as cybersecurity and how these two are interlinked. So put together a slide deck that's really just a very surface level overview about what blockchain technology is, how it connects to cybersecurity. And so we'll be running through that slide deck, and we'll have a Q&A session at the end. But if you have questions in the meantime, I'm happy to answer them as we're just going through the deck. But again, it's very surface level, so it's something that any teacher should be able to kind of grasp, at least conceptually, and then be able to share this information with students. There should be a lot of fun. So thanks again for having me. And let me see. All right, hopefully you guys see the screen share. Okay. So the title of the presentation, Unlocking Blockchain, How It Works and Why It Matters. So this is sort of, again, a beginner's guide for blockchain and cybersecurity and how these are linked. So the agenda, of course, would be a good teacher if it didn't cover like the agenda. And what we're going to cover today in this slide deck, this presentation is, what is blockchain and why does it matter? A lot of times people have heard this term before, but they really don't know anything about it. How blockchain works, just really the functionality at a very basic level. We hear the term, but maybe you don't understand like exactly what it's happening, like how it's being created, like what is a block, what is a hash, some of these things. Proof of work versus proof of stake. So there's two major kinds of blockchain that exist right now, and we'll talk about those. Cryptography and its role in security. Of course, this is where cybersecurity really comes into play, and cryptography is at the core of what blockchain is and how it operates. And then, of course, those cybersecurity connections between blockchain and some real world examples, and then just sort of the future of blockchain. And we'll open it up for any kind of questions that you may have at the end of it. So what is blockchain? Blockchain, quite simply, is just a digital ledger that stores transactions securely and transparently. So any kind of blockchain, when you're looking at the data, you can actually see in any given block what is in that block. So everything is completely transparent. Now, we use a term in this industry called pseudonymous or pseudonymity because you're normally, instead of it saying like my name, Ryan Hazinski, it'll just have an address that maybe starts with a 0x or BC1 in the case of Bitcoin or something like that. And so it just an address is sort of the identifier. And you can see the various addresses that sent transactions and data into a particular block. You can kind of think of it as like a shared notebook. So if, a probably better example nowadays, of course, is just something like a Google Doc, where an entire team of teachers might be working on a single Google Doc. And so the people are just adding something to it in real time. But in this shared notebook, everyone can see the same entries, or everyone can see the Google Doc that they're working on in real time. But in the case of a blockchain, no one single person has the ability to edit it or change any of the entries. And that's one of the things that's key feature with blockchain is that it's immutable. So it's some of these key traits: decentralized, there's no single owner. It's immutable, so it's tamper-proof. It really can't be changed. And it's distributed, meaning there is many copies across a number of places. Most of these blockchains have thousands of nodes that are running all over the world, and each one of these nodes has a copy of that blockchain in its entirety. So the example, of course, Bitcoin is something that people are certainly familiar with in today's day and age. It's certainly grabbed a lot of headlines over the years. We're moving toward an era of regulatory clarity here in the United States. And we talk a lot about Bitcoin. You can see it being now openly discussed among investment advisors like BlackRock, Fidelity, State Street, some of these others. And it's the first fully functional blockchain that launched in 2008. Talk a little bit more about it a little later. So why blockchain matters today? First and foremost, the use that people often think of immediately is cryptocurrencies or just crypto for shorthand. And so this might be something like Bitcoin and Ethereum. But blockchain itself is the underlying technology. So a lot of times people think blockchain and crypto are synonymous, that it's the same thing. But blockchain is sort of just the actual technology. Crypto is only one particular use case. It's used for supply chains, and I'll give you an example a little bit later. We'll talk about IBM. It can be used for voting. And then, of course, healthcare data is something that we're seeing a lot of use case for blockchain as well. So it reduces fraud by making all transactions transparent and permanent, like I was saying in the first slide. Because of these things, you can look at any chain. You have what are called block explorers. You'll be able to search in a particular block. You can find a particular transaction. And again, they're permanent because in every, like in the case of Bitcoin, a block happens every 10 minutes. In the case of Ethereum, it's every 12 seconds. So you can just think of it as a block being proposed that has all the data, and then another block gets added to the chain, another block gets added to the chain, another block, and that goes all the way back to the very beginning of that given chain. So it's always going to be permanent. This is, of course, is going to foster trust without having these intermediaries, right? This is one of the things that you hear a lot about in the blockchain world is disintermediation, separating unnecessary middlemen, because that's just creating points where a lot of times value is extracted, especially when you're talking about financial transactions. So in the case of cybersecurity, however, this is really just protecting data from being tampered with. And that's a huge kind of key connection to cybersecurity. So Walmart uses blockchain to track food from farm to store. This is actually a partnership with IBM. So not all blockchains are public blockchains that need to be reconciled with like anybody looking on a block explorer. Sometimes they're private blockchains, but they're using the same underlying technology to actually accomplish some kind of goal. So in this case, this is able for them to just prevent any kind of contamination when moving things from farm to table by being able to track all this on a blockchain. So how it works, just in the most basic level, as I said with my little hand example, transactions are grouped into blocks, hence the name blockchain. So think pages, going back to the notebook example, just like a page in a notebook would be a single block. And then pages are linked in a chain using cryptography. So this is what holds it together. And if you could think of it, that's the notebook example, sort of the spiral would be the chain that kind of connects all of these pages together. And then the network of computers, often just shorthand known as nodes, they verify and they add to each block. So as a block is being proposed by one of these nodes, what happens is whoever is the first to propose the node, after so many confirmations, as they're called, the rest of the chain will take on all of that data. So it's just every other node is verifying that the transactions that were made into that block is correct. And then everybody gets that updated copy. So you can imagine this gets proliferated all around the world through thousands of nodes across time. So inside the block, now, depending on the type of chain that we're talking about, you actually have limits for how big or how much data a block can store. Bitcoin very famously is quite small. We're talking just like a small amount of data or memory in a block, whereas newer chains can hold a lot more. So usually data such as transaction details, like Alice sent Bob $10 worth of Bitcoin in the case of Bitcoin. The hash you could think of as like a digital fingerprint. So this is the unique identifier for any given block. And I'll show you a short video a little bit later in the presentation so that you can see how difficult these hashes are, or how encrypted, I should say, how difficult it would be to break from a cybersecurity perspective. So the previous hash is going to link the prior block, and that's what kind of forms the chain, is that each hash has to match up with the next one in the sequence on the chain itself. And then a timestamp and nonce is just to help secure and verify the block. And this is important information if you're looking on a block explorer. So again, you think of that hash as sort of the digital seal, if you went back in technology, if you're a world history person, you think about, how royal letters were sealed with a wax and a stamp, so you knew it was something that couldn't be tampered with. This would be now just the hash is sort of something very similar on a blockchain. And so if you change anything in that hash, the rest of the chain breaks and it doesn't make any sense. And so the nodes would discount that block and say, okay, this does not, it is incorrect information, because they all have to form consensus on what counts toward that overall. Now, the next piece is decentralization. So kind of moving through those key traits, what we see is that all of these nodes are going to be spread out. So the big point with blockchain in general is that instead of having a single point of failure, now this is really well timed for us to have this webinar, because just, I think it was yesterday or 2 days ago now, there was a major AWS outage. So when you think about Amazon Web Services, that's a centralized entity. You're talking about one company that is a single point of failure that can disrupt services throughout the globe if they're dependent upon that particular server farm or what have you. And because they're so interconnected, that creates a problem. When you have a decentralized system, because there is no single owner and each node has a copy of the record, you prevent this from happening, because you could have single instances of nodes, or maybe even many. You could have hundreds of nodes go down, but because there are thousands of them all over the place, you really won't lose the chain itself or the data. So it lives on, and this is kind of what I said in the very beginning. I'm the head of protocol partnerships at an infrastructure provider. This is what our company does. We effectively run many different kinds of blockchains on different servers, but we often always have what are called failover nodes. So like if a node goes down, it automatically just reroutes to another node in another data center, and it comes online and continues to run the chain. So this is a quite common setup in many blockchain infrastructure providers, where they're going to have multiple copies of any given chain running at all times. So that way, should one fail, it's not a big deal. The chain just carries on and continues to do its thing. So nodes, you could just think of as computers. That's like sort of a shorthand for just, any kind of node in a network, and that's going to store and validate that blockchain. So as I was saying earlier with the notebook example, the only way you can change the chain is through what's called consensus. Nodes have to fundamentally agree on what is being put into a block and the order in which those blocks compose the chain. If the nodes don't agree, what happens is that particular node gets kicked off. And over time, depending on how fast the blockchain is, you get multiple confirmations. So a lot of times, if you were to send some data on a blockchain, usually depending on said chain, you might need X amount of confirmations before that transaction, is considered finalized. Very often it might be just as few as two, depending on the layer of security. Sometimes they may want 6 or 10 block confirmations, and depending on the speed of the chain, in the case of Bitcoin, it's slow, it's old, it's clunky. It's a 10-minute block. If you need 6 confirmations, it'll be an hour before that block is officially accepted as part of the canonical chain. In the case of something like Ethereum, which is every 12 seconds, you might only need 10 confirmations, but that's only really, 2 minutes because it's 120 seconds. So consensus happens as all of the nodes come together and agree that this is the data that's packaged into a given block. Now, why this is important is because it makes it nearly impossible to hack. Blockchains are super secure, and we'll probably talk a little bit about this at the end of the presentation about why this is relevant for the future. One of the terms you often hear in the industry is Web3. So I'm 50 years old. I remember when the internet just started, right? And if you're old enough, you recall a point at which, in the 90s, we had what we would call Web 1.0. Everything was very static. You went to a website. It was just like a glowing billboard. It might have had some information. You really couldn't interact with it. That started to change at the beginning of the 21st century. Of course, first, probably most famously with Amazon, because they were selling books and you could make an order online, and there were just some early functionalities that crept into that part of the web. And then now Web3 is sort of blockchain-based internet. So over time, I think what will probably happen is, because people think blockchain is so daunting, it'll probably be abstracted away, where these blockchains will all start to be interlinked with one another over the coming, years, and probably especially with the AI continuing to, I think we're already starting to see a lot of convergence between blockchain technology and AI. And so a lot of this will probably be abstracted away where we'll inherit sort of the additional security that you get, the guarantees through blockchain and decentralization, but without the clunkiness of the user interface and the user experience that most people have now. But most importantly is just that it's a more secure version of the internet over time. That's really what's ultimately being architected. So whereas in a case of cybersecurity, if you can hack into a single system, this is funny. You guys are all educators, right? The whole the kid breaking into the computer school system to change the grades, right? And then the report card gets spit out and so on and so forth. And it's easier to do when you have sort of a centralized database that is controlled by a single entity. That's virtually impossible when it comes to blockchain technology. So, because if in the case of a bank, you might be able to compromise customers' accounts because there is a single server, but in the case of blockchain, imagine if that data was held everywhere and no one could really, even if you change it on one, it's not going to be accepted as the correct data because there's no consensus. Okay, so the two major types, I'm going to pause here because I know I'm flying through these things. I know we have a Q&A section at the end, but do you guys have any questions at this point? Am I going too fast? Do you want me to slow down? Everybody good?
It's all good here, Myron.
Okay, awesome. I just wanted to make sure. Um, so two major types of blockchains. So you have proof of work and proof of stake. Proof of work is Bitcoin. Again, this is one that people or at least have some modicum of familiarity. They've heard the term, they understand, they see it maybe in headlines and financial news and so on and so forth. All blockchains originally were constructed in this way. So in a proof of work system, you have what's called a miner. And a miner solves these really complex mathematical problems to generate blocks. The original version, of course, is Bitcoin, and it uses an encryption algorithm called SHA-256. And I'm going to show you a video on SHA-256 in a few slides. That video is interesting because it shows the level of computation that's required in order for people to actually access a block. SHA-256, and interestingly enough, was actually developed by the NSA. So, one of our biggest organizations in terms of like national defense and national security agency, like they're the ones who actually developed this particular algorithm, and then it was employed in the Bitcoin network. Now, as miners work and they're kind of racing against each other to figure out what's in the block, by accessing that block, they're rewarded tokens. And these tokens, of course, have real economic value. Bitcoin today is like a whatever 120, 110,000. I don't know what the number is today, but it's over six figures. So every time a miner unlocks one of those blocks every 10 minutes, they're rewarded some Bitcoin plus some transaction fees. So there's economic incentive for them to have the best equipment to do this. So the pros, of course, are that it's incredibly secure. It is virtually unhackable. Probably the one thing that they often talk about as the boogeyman for blockchain currently in today's discourse would be quantum computing. That quantum computing could somehow render the public and private key, which I'll talk a little bit about keys in a couple more slides. It would render those obsolete and should be able to kind of solve that. Again, this is still a ways off. It's not really a concern for today, but in today, right now, proof of work is incredibly secure because it's so hard to actually break that SHA-256 algorithm. Now, the cons, this is often the thing that you hear, is that it's very energy intensive. So this is why you see a lot of Bitcoin farms that are done with renewable energy. There was a big article, I think it was either Nepal or Bhutan, I forget which one of those countries, is they generate a lot of hydroelectricity. And because they're not a terribly wealthy country, they were actually using it to mine Bitcoin. Same thing we see in China. In the United States, there are solar farms now that are dedicated to generating energy so that they can use for Bitcoin mining. So this is probably the biggest thing that's a knock against proof of work. It's incredibly energy intensive. So Bitcoin, as I said, uses proof of work, miners race to solve that puzzle first so that they can unlock the economic reward. Now, most blockchains today, like, and to give you an example, like my work, we do not do proof of work at all because it is so energy intensive. It requires special machines. We don't touch that stuff. Most blockchains at this point use what's called proof of stake. And the difference is in a proof of stake network, instead of having these very specific miners that are only do one particular thing, you can use general purpose computers and they can just run the node. And the reason that they're being secured is through economic security. And the reason it's called stake is because people put their tokens at risk. So by running a node, you usually have these crypto tokens that'll be staked to a node, and then that gives them the power to actually solve a block and produce it for the chain, and you earn rewards in turn. But if a node is malicious or you do something wrong, you can actually get slashed. So this is why it's called stake, because you're putting up your economic stake and you're saying that I can perform this operation and do it in a manner that's going to be safe. But if you do something wrong, you can get slashed and you lose some of your funds that you would use to back the node. So validators stake their own tokens to secure the network and propose those blocks. And then if you're someone who's not running a node, you can just delegate your tokens to that particular validator. And then you're basically earning a part of the rewards that the validator's earning. In some, but again, not all proof of stake systems, the more tokens backing a node, the better chance it has to produce a block. They're not all set up this way, but some of them are. So the pros in this case, very, very energy efficient. So we're talking a 99.5% energy reduction, and it's also much faster. So almost all of the chains now that run on proof of stake networks have, sometimes as little as a second for a block. So the blocks can be really short. The cons, of course, is that you can have, too much stake gets acquired at the top of the chain, or maybe large node providers are actually the ones who are getting up. There's like an agglomeration of stake, so they're getting the lion's shares of the rewards. And in many of these systems, the tokens also act as governance. So you can enact change on the chain through these governance tokens. So there is that risk, of course, is that they accumulate too much and decentralization becomes an issue. So that's kind of one of the cons. And then, of course, almost all of them, as I was saying earlier, are proof of stake networks, Ethereum, Solana, some of these. And Ethereum itself was originally a proof of work, and then it transitioned to proof of stake back in 2022. All right, so the key differences, just as a quick kind of primer, energy use, very high versus very low. The speed, proof of network is slow, right? One block is every 10 minutes or thereabouts. Proof of stake is very fast, usually in just a matter of seconds. Security, they're both strong, but proof of work, is pretty much borderline impregnable. And the reason that proof of stake would still be tough is that you would need to command over 51% of the chain. So in the case of Ethereum, the chain is worth 500 billion. You would need to get, more than half of that economic value and then be able to commandeer the chain. So it basically is almost impossible. So, and you also scales a lot better. Okay, now this is more into the math of why this all works. And now we're getting kind of into the heart of cybersecurity and how this is related to blockchain technology. So cryptography is a term I'm sure that you've heard. Many of you have probably, think about the Enigma. You may have seen that film where, cryptography is used to kind of create codes. That was very common in World War II. So messages had to be decrypted. So anytime you hear that crypt word, like encryption, decryption, when you're talking about cybersecurity, it all comes back to cryptography and the math that secures the data and that ensures that you have trust. So this, again, makes blockchains tamper-proof and really authentic because you can verify the data is correct because everything is encrypted on the chain. And so you have two key types, which we'll talk a little bit more in depth. Hashing, which is the digital fingerprints. Remember, that's what kind of connects the previous block to the next. And then you also have digital signatures. And this is proof of ownership, or what's sometimes called a private key. And I'll break that down in a second. So how this connects, of course, to cybersecurity is that it protects against fakes and hacks. And so you can prove that the data is authentic. So cryptography, excuse me, is sort of the glue that binds the blockchain together. That's probably the easiest analogy to describe that. So in the case of public key cryptography, think of a public key as a mailbox. Anybody can send anything into that mailbox. So just like in the image you see here, you have your open slot on the mailbox. People can just put in whatever you want. You probably don't want the junk mail that comes to your house. The same thing happens in blockchain, believe it or not, where I can go into one of my wallets, which would be effectively like the mailbox, and I get random things just dropped in there. Now, many times it could be something where someone's trying to scam me, and most of the wallets do a very good job of just hiding things that may seem malicious, but it is a public receptacle in the sense that anybody has that address. So very often it's if you downloaded a wallet and you started something on an Ethereum based chain, it's going to start with a 0x. And then it's just a long string of letters and numbers. So it's nothing that's particularly identifying, because if you go back to the beginning of the talk where I was saying things are pseudonymous, you can trace a wallet to a particular transaction or many transactions on chain, but you might not necessarily know who owns the wallet itself. So the public key is the part that anybody can see. The private key is the part that is critically important. This is what you need as an individual to ensure that your data is sovereign, that you have the ability to send things away from any given wallet, send data. You can make signatures, digital signatures that maybe authorize a connection to a website, and many other things that it does. So this is really used for signing the transaction. So if you had a wallet and you're connected to a blockchain, when you're actually going on to sign something, you usually have to put in a password, but the key itself is something that only you control, and you don't want that to ever fall into anyone else's hands. So it keeps your identity safe, but it also proves that you're the owner of that particular key because you have the ability to sign a transaction. So if, again, talking about cybersecurity, losing your private key is like losing the key to your house, right? If you lost your house key, think about what that would mean and your inability to get in there. I mean, granted, maybe not in a world where everybody has pin locks now on their doors. They can just punch in a code. But, like when you were younger, if you only had a copy of the key to the house, and that was the only way to get in, if you lost the key, then you can't get into your own home. Or worse yet, if somebody actually got a hold of your key, now they can get into your house, they can get into your contents, and so on and so forth. This is why having that private key is so critical. Okay, now we talked a little bit about this throughout this. This is, I probably at the very beginning of the talk introduced myself as a bit of a nerd. I taught a lot of different subjects when I was a teacher: English, social studies, mathematics, did IB. It was actually my IB students who introduced me to this particular person on YouTube called 3 Blue 1 Brown. Apparently he's a mathematician, and he does a lot of great work in trying to explain a lot of different concepts, not just things that relate to blockchain. And this is sort of a short piece that he added that was sort of a side quest, if you will, to his main talk on Bitcoin, which is excellent. It's about 17 or 19 minutes, and it kind of gives you a very detailed breakdown of Bitcoin. But this is a piece where he's just talking about how secure SHA-256 is, or 256-bit security. So a lot of times when you're sending things that are encrypted, they talk about the level of encryption that it has. And this has sort of become the industry standard. Many times for many years, it was 128-bit encryption, which is still pretty strong. 256 is borderline impregnable, as you'll see. So encryption just scrambles that data, again, kind of so only authorized people have access to it. And then hashing creates that unique fingerprint. So I'm just going to hit play. It's about 3.5 minutes, but I think it'll give you a really good understanding of just how powerful this particular encryption is.
In the main video on cryptocurrencies, I made 2 references to situations where, in order to break a given piece of security, you would have to guess a specific string of 256 bits. One of these was in the context of digital signatures, and the other in the context of a cryptographic hash function. For example, if you want to find a message whose SHA-256 hash is some specific string of 256 bits, You have no better method than to just guess and check random messages. And this would require, on average, 2 to the 256 guesses. Now, this is a number so far removed from anything that we ever deal with that it can be hard to appreciate its size. But let's give it a try. 2 to the 256 is the same as 2 to the 32 multiplied by itself 8 times. Now, what's nice about that split is that 2 to the 32 is 4 billion, which is at least a number we can think about, right? It's the kind of thing you might see in a headline. So all we need to do is appreciate what multiplying 4 billion times itself 8 successive times really feels like. As many of you know, the GPU on your computer can let you run a whole bunch of computations in parallel incredibly quickly. So if you were to specially program a GPU to run a cryptographic hash function over and over, a really good one might be able to do a little less than 1 billion hashes per second. And let's say that you just take a bunch of those and cram your computer full of extra GPUs so that your computer can run 4 billion hashes per second. So the first 4 billion here is going to represent the number of hashes per second per computer. Now, picture 4 billion of these GPU-packed computers. For comparison, even though Google does not at all make their number of servers public, estimates have it somewhere in the single-digit millions. In reality, most of those servers are going to be much less powerful than our imagined GPU-packed machine. But let's say that Google replaced all of its millions of servers with a machine like this, then 4 billion machines would mean about 1,000 copies of this souped-up Google. Let's call that 1 kilogoogle worth of computing power. There's about 7.3 billion people on Earth. So next, imagine giving a little over half of every individual on Earth their own personal kilogoogle. Now imagine 4 billion copies of this Earth. For comparison, the Milky Way has somewhere between 100 and 400 billion stars. We don't really know, but the estimates tend to be in that range. So this would be akin to a full 1% of every star in the galaxy having a copy of Earth, where half the people on that Earth have their own personal kilogoogle. Next, try to imagine 4 billion copies of the Milky Way. And we're going to call this your gigagalactic supercomputer, running about 2 to the 160 guesses every second. Now, 4 billion seconds, that's about 126.8 years. 4 billion of those, well, that's 507 billion years, which is about 37 times the age of the universe. So even if you were to have your GPU-packed kilogoogle per person multiplanetary gigagalactic computer guessing numbers for 37 times the age of the universe, it would still only have a 1 in 4 billion chance of finding the correct guess. By the way, the state of Bitcoin hashing these days is that all of the miners put together guess and check at a rate of about 5 billion hashes per second. That corresponds to 1/3 of what I just described as a kilogoogle. This is not because there are actually billions of GPU-packed machines out there, but because miners actually use something that's about 1,000 times better than a GPU: application-specific integrated circuits. These are pieces of hardware specifically designed for Bitcoin mining, for running a bunch of SHA-256 hashes, and nothing else. Turns out there's a lot of efficiency gains to be had when you throw out the need for general computation and design your integrated circuits for one and only one task. Also, on the topic of large powers of 2 that I personally find it hard to get my mind around.
Okay, so hopefully that gives you some sort of sense of scale for how big that actually is when we talk about SHA-256 or 256, just bit encryption in general. So just the numbers that are required to actually calculate something like this. And the numbers are probably much higher now because this video is some years old in terms of the hash rate of the Bitcoin network, which has only continued to grow, and the ASIC miners have only become more and more advanced. So ultimately, blockchain enhances security, creates those immutable records. There's no single point of failure. Cybersecurity protects the blockchain from hacks, phishing, or code bugs. Together, they create trust in a digital world. So if blockchain is the safe, cybersecurity is the alarm system on that safe. Now, blockchain, as I was saying earlier, is sort of a way to boost security, and I think ultimately will rebuild the web through these newer, more secure protocols. It reduces data breaches because there's no central server to hack. There's no single point of failure. As I said with the AWS example from the other day, it enables secure voting or identity protection, verification rather. Smart contracts. Now, this is something that was only developed on Ethereum and later. These are automatic agreements that are based on code. So you don't need to do anything. You're basically just telling the blockchain you're going to interact with your wallet. You're doing something on a smart contract. The contract just does the code, and an output is generated on the chain. So you're doing that process of disintermediation and getting rid of them. So an example what we're seeing with healthcare data, especially, is patients control their own personal health data and provide access only to parties who need it. All right. And of course, any system has risks. Some of these things I alluded to earlier. The 51% attack where hackers take control of the majority of the network. Again, it's nearly impossible to do due to the cost. Private key theft, something that I already talked about previously, where now if you lose that digital key, that private key, your wallet is compromised and the contents could be taken. So sharing your seed phrase or leaving it in a vulnerable place, anything like that could get it taken. Smart contracts are not perfect. There could be bugs, and this is why we need, especially from a cybersecurity perspective, third parties to audit code and to look at them to make sure that the smart contract is going to do exactly what it says it's going to do. Because, in fact, I would say this is probably the biggest risk in blockchain right now. A lot of times, if code for a smart contract isn't thoroughly vetted, usually very smart people will find a way to exploit a particular bug and do something. The first best example of this, of course, is the DAO hack in the original version of Ethereum when it launched. Basically, there was a way where they figured out that they could withdraw funds from it. And so they removed about $50 million worth of the ETH token. And this actually created a whole new chain because what they then decided to do was vote, and they forked the chain. So they took the old version and they created a new block, and they started a new version of the chain after fixing this code. So the Ethereum Classic chain is the original chain that was launched, and the Ethereum, that's the second biggest crypto and blockchain network right now outside of Bitcoin, that then became a point of contention, over 10 years or almost 10 years ago, because the phrase code is law was something that was talked about at great length, that if this is the code, this person didn't do anything wrong. They just actually did exactly what the code allowed them to do. But then they patched that code and that bug, and they forked the chain completely. And so, again, third-party audits, this is where cybersecurity is going to come in, because you want to verify that these codes are, set up in such a way that you can't have these exploits. Multi-factor authentication is something that also gets talked about a lot as well. So some real world examples, I've talked about Bitcoin plenty. This was sort of the very first blockchain. It was a digital currency without banks. As a quick funny anecdote, when I was a teacher, the first time a student ever brought up Bitcoin to me, I Googled it. I saw things about like buying drugs on the dark web and Silk Road and all this stuff. This was probably back in 2012. And then it was in 2016 when I was helping one of my IB students who wanted to actually create a 501c3. And he said, "Oh, I'm going to build a blockchain. We're going to do everything on a digital ledger." I thought he was just some smart kid who invented this thing. And then he came running up to me at the end of his senior year in May of 2017. He's like, "Hey, have you been paying attention to Bitcoin?" I'm like, "Why do you care about Bitcoin?" He's like, "That's the first blockchain. That's the first digital ledger." And that was what kind of made the light bulb click and made me read the white paper and start really learning about this technology. So again, it uses proof of work, public key cryptography. Chain itself has never been hacked. Again, you saw through the code how SHA-256, how difficult that would be. And then it's now the market has evolved considerably. It's become something that even Wall Street, they have ETFs and everything else. So the Bitcoin has certainly changed over the 15-ish years of its existence, or now actually coming up almost on 17 years. And no one knows who it is. Satoshi Nakamoto is the pseudonymous creator. It could be a single person. It could have been a group of individuals. No one has any idea. Satoshi used to be very active on the early chat boards back in 2010, 2011, and then just famously disappeared. And his wallet holds probably the most Bitcoin to this day. Ethereum and beyond, those proof of stake chains, again, the big iteration here was the ability to run these smart contracts, which allowed for decentralized finance through dApps or decentralized applications. NFTs, they were all the rage a few years ago. This is my boss's Bored Ape Yacht Club NFT. I had to honor Ray in the presentation. So you have digital art that is held on chain and can be stored in a given address. As I said, the supply chain example with Walmart and their partnership with IBM, where they're doing the food trust, cybersecurity, because you have such secure data sharing or these identity systems, and then NFTs, as I said in this example, you can prove ownership that you own a particular piece of digital art. And then the future of this altogether, Web3, I kind of alluded to that title before and what it means, sort of the decentralized internet, private blockchains. We're starting to see some banks experiment with private blockchains just so that they can move money digitally on their network in a secure manner. JP Morgan is doing this in a partnership with Avalanche, and they created a private network called Onyx. Zero knowledge proofs for privacy. This is something that's become sort of all the rage in blockchain. Zero knowledge, where you can sort of shield the information that's contained in a transaction and you don't really know. It's sort of like a black box if you wanted to just make sure that something was very secure. Of course, the challenge is regulation, which we're currently going through those growing pains right now with the United States, where we passed the Genius Act for stablecoin legislation that was earlier, and now they're working on a market structure bill called Clarity. And then AI and blockchain, as I said earlier, we're starting to see a strong convergence between these two modalities and how they're growing together. And this could give us much greater threat detection in advance. And then, of course, you should be somebody who could play around with these things. I'm not very technical. I'm not very sophisticated, but you can go onto a test net. You can download a wallet. You can try out the technology for yourself and just see what it's like. And if you have questions, it's also something you could introduce to students, and you could do it in a way where they can just kind of play around with the technology and get sort of an understanding of it. But as I said, much of this I think is going to be abstracted away in the coming years to where people will be using blockchain in the background but not even realizing that they're doing so. So again, blockchain, secure, decentralized ledger that uses cybersecurity and cryptography. It's used for money, supply chain tracking, voting, healthcare systems. And we're probably going to see more use cases develop in the future. And so I would suggest, just download, try a wallet. You could do a little bit, if you're coding, you could probably check out some test nets and build some stuff, especially with the help of AI. You can do a lot now. But I'll pause here. I know we've probably eaten up most of the time, but happy to answer any questions that you may have. And outside of that, I'm just going to stop sharing.
Ryan, that was fascinating, man. Thank you so much for your time and sharing your expertise. Really interesting to hear about kind of how that technology works and the different applications, even beyond crypto, is remarkable. I'm going to stop the recording now so people can ask questions without feeling that they're going to be on film, and then we can open it up for questions.
All right. Thanks, Jeremy.